A little homework help for Unit 5, Lesson 19, talking about spheres today. Skip over the first couple of equations. We're going to get, or questions, we're going to get to these ones. I think this one will take a little bit of a picture to be able to understand, but a hemisphere fits snugly inside of a cylinder with a radius of 6 centimeters, and a cone fits snugly inside of the same hemisphere. I think what we can look at here is if we start with the hemisphere. Remember, a hemisphere is half of a sphere. If we talked about fitting that hemisphere snugly inside of a cylinder, we're talking about a cylinder would fit approximately right here, and we have the base of the cylinder. And what we would see with that is that the diameters would be the exact same, and that the bottom of this hemisphere would be the same height as the sphere. Okay? And then we're talking about putting a cone inside of here. I'm hoping that by doing different colors, this helps you to see that what we're really looking at here is we're looking at a cone inside of a hemisphere, inside of a cylinder. And what we need to recognize with these is that if they all fit snugly inside of that cylinder, then we're going to calculate them all as though they have the same radius and that they would have the same height. The key thing about this, you might be saying, well, I don't know the height of the cylinder, so how can I find anything like that? I don't know the height of the cone. Keep in mind that on a hemisphere, the radius from here to here is one value, and since it's a sphere, that's the exact same value for the height, quote unquote. The radius extends to any edge that we're on there. So when we think about this, the radius for all three of these figures, radius is equal to 6 on all of them, and the height for the cone and the cylinder is also 6. I hope that's enough information to help you with this one to understand how to solve these. So when we look at the very first one, it says, what's the volume of the cylinder? Okay, when we use the volume of the cylinder, the volume is equal to the area at the base, which is a circle, pi times the radius squared. And then I know that the volume is equal to, by substitution, pi times the radius of 6 squared times the height of 6. And we should be able to find that volume of the cylinder. Based on what we know about the formula for the volume of a cone, I should be able to think pretty quickly with this that it has the same radius and the same height. So that means that the volume that I have should be 1/3 the volume of that cylinder that we just did. So really, I shouldn't have to redo all this work because it's the exact same as right here. All I have to do is divide by 3. The final step of this will be estimating the volume of the hemisphere by calculating the average of the volumes of the cylinder and the cone. So we're going to take the volume of the cylinder plus the volume of the cone, I'm going to put CY there, plus the volume of the cone, and then we'll have to divide that by 2. So be really careful that you add and you divide by 2 carefully. These are not variables in any way. This is just a measure, a way of marking it. It would probably be more appropriate for me to say that the volumes would be recognized as volume of a cylinder would be the first value and the second value. So the volume of the cylinder plus the volume of the cone, and then divide that by 2. Remember to keep your answer in terms of pi. On the next question, we'd find the measurement given the radius or the diameter. We are looking again here at a hemisphere. So please keep in mind that a hemisphere is half of a sphere. So at the very end, you have to think about if you find the volume of a total sphere, you need to make sure that you take that volume and divide it in half. All right, please keep that in mind as you get going with this. Also remember that when we're finding the volume of a sphere, the volume is equal to 4/3 the area of a circle, except we're going to cube that radius. So 4/3 times pi times the radius cubed. When we go into the next one, we need to consider that when we find part B, that the hemisphere's diameter is, or what is the hemisphere's diameter if the radius is 1,000 thirds. Well, think about that. The diameter is equal to twice the radius. So if we're given a radius, keep that in mind when we find the diameter, that we have to double it. And the hemisphere's diameter would be directly related to the radius. Part C, I want to find the hemisphere's diameter if the radius is given as 9 8/1000. Think about it again. Hemisphere's radius, well, if its diameter is 6 centimeters, hemisphere's radius, if the diameter is 1,000 thirds, pay close attention. You are now finding that diameter is 1,000 thirds is equal to the diameter. Okay, be very careful with that one because now we're going the opposite way. And then again, figure out the radius when you know what the diameter is. All right, so be careful, read carefully, but remember diameter is equal to twice the value of the radius. The next question, after almost running out of space on her phone, Elena checks with a couple of friends who have the same phone to see how many pictures they have on their phones and how much memory they take up. The results are shown in the following table with number of photos and then followed by the memory that's used. Question comes down to, could this information be reasonably modeled with a linear function? I'm going to have you look at the next problem, preview that next problem. It says Elena needs to delete photos to create 1,200 megabytes of space. Estimate the number of photos she should delete. Having a look at this question should give you a preview that yes, this is a reasonable amount that's modeled here. But in order to understand this, we have to recognize a couple pieces of data. First and foremost, I want you to think about constant rate. This is a proportional value because if you have 0 photos, there should be 0 memory used for that. And so what we really want to look at is comparing how much memory is being used per photo as we look at these values, meaning comparing this one to 10,106 divided by 3,148. That's a 4, I promise. And then compared to 6,037 megabytes divided by 1,875. And as we go and look at these values and compare them, we see that 8,072 divided by 2,523 gives us an approximation of 3.2 megabytes per picture. So hang on to that value, 3.2. About 3.2, just slightly different. The previous one that we saw was 3.2 or 3.199, whatever it was. It was really close to that. And then finally the last one, 6,037 divided by 1,875 is again about 3 2/10. So looking at the reasonableness of those values, we do see something that's approximately a constant rate. Make sure you discuss that right here when you talk about that. Could this information reasonably model a linear function? Yes, comma. You need to talk about that constant rate and why we can say the constant rate is fairly close to that, and then answer the question for how many photos need to be deleted to make 1,200 megabytes of space. And that's it for the homework. Thanks for tuning in. Let me know how I can help.